All right, so here we go with 11.2, paper 2 questions on power generation and transmission. Okay, so number 1 includes a transformer, but really all of the parts of question really have more to do with the capacitor, and capacitance is 11.3. So I'm going to skip number 1 and go to number 2, which is talking about a transformer, but then it's asking for the number of turns on a secondary coil that is 11.2. Okay, so for 2, we have a transformer connecting 110 alternating current to a 15 volt direct current. What's this garden lighting system? I'm assuming that's direct current. And that has 8 lamps connected in parallel. So for the transformer, primary coil is 3,300 turns. I just did the ratio of the primary coil to the secondary coil is equal to the ratio of the voltages, primary to secondary. And I get that the number of turns in the secondary coil is 450, which agrees with the mark scheme. Ding. All right, so 2B. 2B is the total resistance of the lamps. That's not really, you can calculate that stuff, but that's not really topic 11.2. Let me actually, hold on. So 1 is out. No, 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 no. I missed that one. No. And no. 2A, yes. 2B, no. 2C, yes. Current in the primary of the transformer, assuming it's ideal. Okay, so 2C, this involves some power calculations, but also involves the transformer ratio of turns to current. So first, I'm trying to figure out the current in the primary. In order to do that, I need the current in the secondary. In order to figure out the current in the secondary, I need to know the total current for the circuit. I know the total voltage is 15 volts. They're in parallel, so they're all the same voltage. But the total power, there are 8 lamps of 35 watts apiece, and so it's 280 watts total power. So therefore, the current is 18.6 amps and change. And then once we know that, that's the current in the secondary. I know the ratio of the coils, 450, or 3,300 to 450. And I can solve for the current in the primary, which winds up being 2.5 amps, which agrees with the mark scheme. So there we go. 2D says, because of flux leakage, why a transformer may not be ideal. What's that effect? I think the mark scheme kind of explains it pretty well. Oh, hold on a second. I'm circling the ones I want. 2C, yes. 2D, yes. And going over here, mark scheme says secondary coil does not enclose all the flux from the core, which makes sense because the core is 3,300 turns and the secondary is only 450. So yeah, that secondary coil is much smaller. And so that's one source of less efficiency. So you could say that the because with an ideal transformer, you're assuming that all the flux is captured. So if all the flux is not captured, then you're going to get less induced EMF. You can say that, or you can get less power, or you can say that the efficiency is less. But yeah, all of those things are less. For this reason, secondary coil does not enclose all of the flux lines from the core. I don't really know how else to say that. All right, 2E, what's this about? So the bob slows down because of Lenz's law. Metal bob accelerates through the magnetic field. There's a change in flux. So Faraday's law says that there's going to be an EMF produced in that bob itself since it's made of metal. Lenz's law says it makes a EMF in the other direction, so an opposing magnetic field. And since it's an opposing magnetic field, it makes an opposing force slowing the bob down. Any kinetic energy loss in the bob turns into heat in the metal, which is what the mark scheme says. Notice there are 4 points, and there are 1, 2, 3, 4, 5, 6 checks here, because they're like alternative explanations, but they pretty much says the same thing I just said. All right, so that was 2E. Oh, I'm going to circle that. All right, 2E. Then let's take a look at 3. We have a rotating coil and a magnetic field. Looks like a generator to me. Okay, so it says explain how an EMF is induced in the coil with reference to Faraday's law of induction. So here's Faraday's law of induction right here. And N is equal to 1 because it's just one coil. But it's like, how is there a change in flux? So it's another explanation question. So EMF is the number of coils times the change in flux over time, and flux is BA cosine theta. Magnetic field strength is constant, area is constant, but the angle is not. As the coil rotates, that angle between the magnetic field and the area vector changes by the rotation of the coil, and that angle change is what causes the change in flux to induce the EMF. They gave us power, they want RMS current. P is VI, so we're solving for I. We just have to get the RMS voltage off of that graph. I can see that the peak value, V peak, right there is 25,000 kilovolts, 25,000 volts. That divided by 2, divided by radical 2, is 17,678. So the power, the 850,000 watts over that 17,678 volts gives me 48 amps worth of current, which agrees with the mark scheme. So 3C talks about a step-up factor, which is pretty much kind of like the voltage ratio or the current ratio. So like this, if I had a voltage ratio of, say, primary being 240 and secondary being 120, then that step-up factor, I'm sorry, primary is 120 and secondary is 240, the step-up factor would be 2. So it's kind of like they're looking at just ratios here between voltage and current and even numbers of coils. And so it's like he wants the power reduction to be 250, so that factor is 250. And so I know power losses are I squared R, related to the current. So I squared power is proportional to the current squared, and current and voltage are directly proportional, so power is also proportional to voltage squared. So if power is proportional to voltage squared, it's looking for the voltage factor. So voltage is proportional to the square root of power. So if the power factor is 250, the square root of 250 is about 16. It's actually like 15.81138, etc. It's close to 16. So if I want to reduce the power loss by 250 times, then I'm going to need to step up the voltage and thus step down the current by 16 times. So that's where the 16 is coming from. And in 3D, I guess they want you to use these axes up here. So let's take a look at 3D. Okay, so 3D. Frequency of the generator is doubled. Nothing else has changed. Draw the graph. So I know if I have double the frequency, I'm going to have half the period. But in terms of the actual voltage output, it's also going to double the max EMF. And the reason why that's true is because EMF, if we take the first derivative of the flux with respect to time, we get that EMF is NBA omega sine omega t. And then I'm looking for the peak values for the graph. So the maximum EMF would mean that the sine of omega t is 1. So maximum EMF is NBA times omega. Omega, of course, is 2 pi times the frequency. And if we double the frequency, therefore we double the max EMF. So if we go up to the graph and take a look, we have, first let's erase what is already there. We don't need that anymore. And so we're going to have a cycle that completes in half the time. So it's going to complete in 10 seconds. So the halfway mark is going to be right there. And instead of having 25,000 volts max EMF, it's going to have 50,000 volts, twice as much. So here we go. And that's what our graph is going to look like. And the mark scheme agrees. Peak EMF doubles and the period is halved. All right. Then now we're moving on to 4. All right, so number 4, we have this lighting system attached to 2 rods. We know the lamp specs, voltage and current for each lamp, voltage and power for each lamp. Power supply EMF, we know the maximum current coming out of the power supply, we know the length of each rod, we know the resistivity of the rod metal. Now 4A we don't actually need because that just gives the radius of the rod. You do that with R is rho L over A, but we're not really going to worry about that right now. And then 4B says, how many lamps can you connect? I actually am going to look at that because I'm going to need that later for where is it? For E, talking about the peak currents in the transformer. And it says with the maximum number of lamps, 4B is where you calculate the maximum number of lamps. So each lamp is 24 volts, 5 watts. Each lamp 24 and 5? Yes. So if P equals VI for each lamp, then I is equal to P over V for each lamp. So I have 5 watts over 24 volts, and the current in each lamp is about 0.21, 0.208, amps. Now it did say that the total power supply current available is 8 amps. So 8 amps divided by the current in each lamp. And that gets me 38.4 lamps. And you can't have 0.4 of a lamp, so the maximum number of lamps is 38 lamps, which does line up with the mark scheme over here, 38 lamps. 4C is a series and parallel circuit question. 4D deals with eddy currents. Let's take a look at 4D before we get to 4E, where we will need that maximum number of lamps. So eddy currents, step-down transformer used to transfer energy to the 2 rods. Primary coil is connected to an alternating main supply, has an EMF of 240 volts. The transformer is 95% efficient. And how do eddy currents reduce the transformer efficiency? And that's for 2 marks. And so eddy currents are what happens, eddy currents in the coil, in the core. So yeah, the eddy currents in the core that produce opposing magnetic fields, which is Lenz's law, and those opposing magnetic fields present an opposition to the current in like a pushback, a resistive force to the primary coil. And so those eddy currents with their opposing magnetic fields that create opposing forces, resistive forces, back EMFs they call them, and that's just going to create heat losses instead of a 100% efficient energy transfer, which is what pretty much the same thing as what the mark scheme says. Okay, so for E, max number of lamps, we determined that was 38 lamps, and the maximum number of lamps, that's 38 lamps, and we know that those lamps are 5 watts a piece, so that winds up being 190 watts total on the load end. Now it says somewhere here, yes, it says that the transformer is 95% efficient. So the output power is 190. So we have, or rather the load side, I guess the secondary, I would call that. Secondary power is 190. So primary power, I'll call that P primary, I guess. Or, hold on. I should say P secondary is 95% or 0.95 of P primary. So 190 watts, which we get on the secondary side, is 0.95 of 200 watts. So in the primary coil, we're going to need 200 watts of power. Now it's not asking for the power, it's asking for the current. So I do know that the voltage in the primary coil has a root mean square value of 240 volts. And so if we do P equals VI for the primary side, using the RMS voltage and the what must be the average power, because we're dealing with RMS voltage, we get RMS current of 0.83 amps. Now notice that the answer is not 0.83, the answer is 1.2, because the question did ask for the peak current, not the RMS current. So let's recall that. So recall that RMS current is peak current over radical 2. So we can do radical 2 times the RMS current to get the peak current of 1.2 amps is what we're looking for. I'm forgetting to circle the ones I want. We want 4D, we want 4E. Let's see. We want 4B. Forgot to circle that. Alrighty. Now we're up to number 5, which deals with a bunch of capacitors, but there is a transformer portion of that, and so we'll come back to that. Alright, let's continue on. We have number 5. 5 is talking about a parallel plate capacitor, and so that's 11.3. We don't want to deal with that just yet. And then
for your convenience, online banking users can often dispute a charge directly from the transaction detail
do
in the
my
activity tab.
Stupid credit card thing at the same time. Tried to prepay for parking on a trip, and then they made me pay twice. Annoying. It's like a few $100s too, so I'm disputing the charge. Anyway, so let's move my phone over there. It's not so loud. And let's see. So we have the capacitor 5B also deals with capacitors. That is 11.3. Also, let's see, 5C. Yeah, talking about the dielectric of the capacitor. That is not for us. But 5D is dealing with a transformer. Let's take a look. 5D. So 5D has a transformer, and we're talking about turns and the coil and relating the voltage. This is easy. This is a one-shot deal for this equation, for this problem. All right, I'm off the phone with the bank. It's what happens when you try to do two things at once. All right, but yeah, this transformer, we had this ratio situation going on, so we're looking for the voltage output on the secondary. So that's going to be the ratio of secondary turns to primary turns times the voltage. Also, one thing that's a little tricky right here is that they're giving the peak value of the voltage, peak value, and they're looking for the RMS value of the output voltage. So when I go for this secondary voltage here is 1200 over 100 times 200, that's 2400 volts. That's the peak. So let's if we're looking for the RMS, VRMS is peak over radical 2. So, and you get 1700 volts when you round for sig figs, which is totally not the right answer. Go me. I think I see my mistake. I said 200. It's supposed to be 220. Maybe if I could read. There, I fixed my math. 1870 volts is the RMS of the output voltage. Yeah, for a second I was confused for a minute. I thought this was a step-up transformer. It's a step-down transformer. No, it is a step-up transformer. It's going from, the primary voltage is, of the AC supply, is 220 volts. And there are fewer coils, fewer turns in the primary than in the secondary. The RMS voltage of the output voltage, the RMS value of the output voltage is 1870, and that is correct. That is the answer. So my approach is right, but I made a math mistake. My bad. But it's all good now. All right. Describe the use of transformers in electrical power distribution as 5E. Let's go from there. 5E. I think that the mark scheme kind of describes the answer. But yeah, so step-up transformers, they increase voltage to go to a higher voltage. But let's also remember the power is conserved, energy is conserved, so power is conserved, and P power is VI. And basically what you want to do is the energy power losses in transmission. What they're talking about there, those losses are I squared R losses, and it's current that really causes the heat losses in the transmission wires. And so by stepping up the voltage, they decrease the required current, and by decreasing the current, then you're decreasing those power losses from heat. And then once you get down to the other side, to the customer, then you go from your high voltage down to your low voltage, because you can have thousands of volts in a transmission line, but you don't have thousands of volts going to a customer's house. And you can still maintain the power, but you can increase the current and decrease the voltage by the use of a transformer and bring it back to more reasonable power and current numbers for that. But I think the mark scheme kind of explains what's going on there. And the three marks, there's the 4 lines here, but the 3 marks they're talking about is mentioning step up and step down transformers, how that works. Why that's done, because it decreases the current, and we're decreasing the current because we're trying to minimize the I squared R losses. And then 6A, state Faraday's law of induction. Again, the mark scheme here. Oh, I don't want green. And the mark scheme does a good job here. It says the size of the induced EMF is proportional to the rate of change of the flux linkage. You can also write that as EMF is negative change in flux over change in time, but you would definitely need to explain the terms. When they say state a law, you can write the law, but just for yourself as a visual, but that does not count as actually explaining what it is. You have to walk through and say what all of the variables are and what the relationships are. So the EMF, that's this, and equal to the rate of change of flux linkage, that is that N times the change of flux over change in time. 6B, we have ourselves a transformer, and it says, explain how the transformer steps down the voltage. I'll say, okay, so a few things. Now, this says 240 volts over here on the primary side. That has to be alternating current. The reason why is because Faraday's law says that the induced EMF is negative N times the change in flux over the change in time, and flux is N, well, hold on, actually I already have the N in there. So that would be the magnetic field strength times the area of the loop times the cosine of the angle between the area vector and the magnetic field. But I need, in order to produce an EMF, I need to change the flux. It's the change in flux over time. So either I need to change and there needs to be a change in something. In order to get an EMF, there needs to be some kind of change. Change in the magnetic field, change in the area of the coil, change in the angle. Like when we rotate the coil, we're not rotating the coil in this case, but we are changing the magnetic field by, so that induced magnetic field I should actually, it's not really, that's getting confusing. I'm going to take out the word induced there. Just the magnetic field of the primary loops, that is changing because the current in the loops is changing. There's a change in current in the primary, and the reason why there's a change in current in the primary is because it's an alternating current circuit. So by that, the current alternating back and forth in a sinusoidal pattern with a constantly changing value, that's going to make a magnetic field strength that's constantly changing in the coil, and that changing magnetic field strength is going to cause the change in flux, which will induce an EMF in the secondary coil. And so that's the first point right there. A varying voltage or current in the primary coil produces a varying magnetic field in that coil. So yeah, in or of that coil, and then that's going to produce a change in flux linkage and a change in magnetic field of the secondary coil. That's the induced in the induced magnetic field in the secondary coil. So the first point actually doesn't have anything to do with Faraday's law. It's just saying that a magnetic field sets up around the primary coil, but then that magnetic field is transferred via the core. That's the like kind of rounded rectangles, you see that magnetic field is transferred via the core to the secondary coil, and that's where the induced EMF is. There would be the secondary EMF, and that induced EMF in the secondary coil is because of Faraday's law. There's also Lenz's law. That means there's going to be some energy losses there because the magnetic field is opposing. So if the current is going one way in the primary coil, the current is going to be going the other way in the secondary coil. And that third point is also, Faraday's law, that it makes a change in magnetic field in the secondary coil, which then therefore induces an EMF in that coil. Now, the reason why the voltage is stepping down, right, and it says comparison of turns is required for marking point 4 because it's stepping down the voltage, there's a difference in the number of coils. So there's a difference in the N count. And if there's a difference in the N count, that directly affects the flux linkage. That's the whole point of flux. That's the linkage in flux linkage. It's the N count. So again, if we look at Faraday's law, where induced EMF is negative N, change in flux over change in time, if there's a difference in the N, you're going to get a difference in the EMF. I mean, that's the entire point of with transformers when we talk about the number of terms in the primary coil over the number of terms in the secondary is equal to the ratio of the EMFs from primary to secondary. So there we go. Speaking of that equation, we have 6C, and so in our secondary coil we wind up with 12 volts. Let me work that out. Let's see that right there, 12 volts. All right, let's keep on moving. How are energy losses reduced in the core of a practical transformer? The energy losses would be to heat, so it's thermal energy. But by using a laminated core, it reduces eddy current. So again, the core is this set of nested rectangles right there. That's the coil, the core. But if we have laminated being the layers, so laminated, that's a layered core, that reduces the eddy currents, and if no eddy currents are set up, then you're not going to get I squared eddy currents. You're not going to get I squared R losses. So yeah, that's the first point, is talking about how they layer the laminator layer the core, and so then yeah, there's no heat losses. So in terms of energy losses, how would that energy be lost? It would be lost as heat. And then 6E is 5E. It's like the same thing. Why do they use transformers in electrical power distribution? The I would say C5E. It's pretty much the same question. It's a little bit. It's instead of 3 points, instead of 3 marks, it's 2 marks, because they give a little bit more details in the 5E than they do in 6E, or rather, the question gives more detail in 6E and requires less detail than 5E does, but it's pretty much the same as 5E. Alright, so 7 has to do with transmission wires, and so 7A we don't need, it's a resistivity question, but 7B, it's a power calculation, but we're going to need to do 7D. So peak current in the cable, if we have P is VI, then the current is P over V, and these are peak values because it says so in the problem. It says that, where is it? Output power of 110 million watts is when the peak potential difference is 150,000 volts. And so we get a peak current of 733 amps for 7B. They're claiming 2 significant figures. I mean, I don't know. I see 110 and 150, so I'm going to claim 3 significant figures. Whatever. But then for 7D, let's see. That was 7B. The power bit per unit length, we're not going to really worry about that. I don't think we need it. But root mean square current in each cable, I can get that off of the peak current. For some reason on the mark scheme, they divided by 2 radical 2. It says response to B, and it's only 1 cable. So we have the peak current in 1 cable. Oh, there's 2 cables. I didn't read the question. Alright, to ensure that the power supply cannot be interrupted, 2 identical cables are connected in parallel, and it says, what's the root mean square current in each cable? Alright, there are 2 cables in parallel, and they're the same cable, so they have the same properties, and they're in parallel, so the current is split between them. Current split between them. So if the current is split between them, and it says find the root mean square current in each cable, it's not 733 amps. It's 733 divided by 2, which is 367 or 366.5 amps. And then divide that by radical 2. And that is 260 amps RMS current. That agrees with the mark scheme. Gotta read the question. Alright, now we have 7E. So it says 2 cables suspended a constant distance apart. How can the magnetic forces between the 2 cables vary during the course of 1 cycle of the AC? So if we go and look at the parallel connection, it's not that for the alternating current, that alternating current is hitting both cables at the same time. So both cables are going to be in phase with each other. So it's not like one cable is going to be completely out of phase from the other cable. Both cables will be in phase because the current is just split between them from the AC generator to the load. So it says the cables attract each other whenever current is in the same direction. Let's take a look at why that's true. 2 different wires. Say the current flow is going from left to right for both of them. Alright, so the blue circles I just do is going to be the magnetic field for this wire, for the first wire. And because of the right-hand rule of magnetic field curling around the wire, if the current is moving to the right, then it's going to curl with up here the magnetic field is coming out of the page, and down here the magnetic field is curling into the page. It's also into the page down here. Now, the same thing is going to be true. I'm going to use a different color. I'm going to use purple. And then doing the magnetic field for the second wire, and also doing right-hand rule for that guy, it's going to be coming out of the page above the wire, and it's going to be going into the page below the wire. Now let's go back up to the first wire there. So now that first wire, the top wire, has a current moving to the left, and it's sitting in a magnetic field from the second wire, from the bottom wire, and that magnetic field is coming out of the page. So if my current is going to the right and the magnetic field is coming out of the page, then the force on that wire is going to be downward. That's going to be a downward force going that way because of the hand rule for force on a wire in a magnetic field. Now if I look at the bottom wire, I can see its current is also moving to the right, but it's sitting in the magnetic field of the first wire. That would be the blue field that I drew. That field is going into the page. And so if I have current moving to the right and that field is going into the page, that's going to be a force going up. And so like the mark scheme said, wires that have currents moving in the same direction are going to attract each other. They have a force towards each other. So you don't need to necessarily derive all that to answer the question, but that is the explanation as to why they said that. So wires attract when their current is in the same direction. And the current will always be in the same direction because they're in phase with each other. Now they're not going to attract when the cycle is at the point when the EMF is 0, because we have an alternating current here. So if it's alternating current, there's going to be points when you have a maximum, and then there are going to be points when you have no EMF. So if there's no EMF, then the force is going to go to 0. So that's where it says force varies from 0 to maximum. And it also says that the current direction is going to be the same but reverses every half cycle. I don't know that that's relevant, because as long as the current direction is the same, they're going to attract. And it's asking, how are the magnetic forces going to vary? So basically we're going to have in one cycle, we're going to have 3 points. Those 3 points where you're going to have no force, where the EMF is 0, and then you're going to have 2 points of maximum force, because it's the maximum EMF of the current, and of the EMF, therefore producing the current through the wire. And so we're going to have maximum force. That's where it says force is a maximum twice in each cycle, and it's 0. Let's say and 0 3 times per cycle. And even though in the 3/4 of the way through the cycle, the current, instead of moving to the right, is moving to the left, still, if the currents are in the same direction, we still get an attraction. So there's not just a force, it says a maximum twice in each cycle. That is an attracting force in all cases. Notice that the mark scheme says award only 1 point if it says that there is a repulsion. There is never a repulsion. There would be a repulsion if the currents were in opposite directions. If current in opposite directions, which, even though both currents go left, right, they're going in the same direction as they're split into 2. It's not like one current's going to go one way and the other's going to go the other way, so there will be no repulsion. 7F says, what are the advantages of using step-up transformers? They already asked that. That's asked and answered in 5E and 6E. 7G is pretty much the same as 6D. We laminate the core. We layer the core to reduce eddy currents and thus reduce the I squared R heat losses. Also be careful. Notice that the mark scheme says do not allow wires are laminated. It's not the wires that are laminated, it's the core. The core is layered. Lamination means layers. When you laminate a poster, you put a layer of plastic on it. So that's what they mean by that. And then we have number 8. We have 8A and 8B. Holy smokes, 8B is 5 marks. And so let's take a look at number 8. So for number 8, it's talking about power generation and transmission. And we have the primary voltage coming out of the power plant. We have the secondary voltage coming from the transformer to the grid. We have the primary current, and it's asking, and the efficiency, and it's asking for the secondary current. So we can do that by a ratio. And don't forget to use the efficiency of 0.96 to get 280 amps on the ideal current of 295 amps. And it's 2 sig figs because the voltage and the current are 2 sig figs. Then for the second part, number 2, or double I, for the same or similar power, we use very high voltage, we can have very low current. Heat losses are I squared R losses, so if we can reduce the current, we reduce the heat losses. That's why they use high voltage for transmission. Also note that the mark scheme says that you have to say heat. You can't just say energy loss. It has to be specifically energy loss as heat. 8B is the last question in this set. Alright, so 8B has this coil rotating in a magnetic field, and it says 8BI, explain with reference to the diagram how the rotation of the generator produces an EMF between the brushes. Well, EMF is negative N times the time rate of change of flux, and flux is BA cosine theta. So let's see, that angle theta is between the magnetic field and the area vectors. And as that coil rotates, that angle is constantly changing, so that produces the change in flux. So that, therefore, the EMF is produced. I feel like that's enough explanation, but it says with reference to the diagram. So, I don't really know what they mean by reference to the diagram. Well, let me check. I didn't actually look at the mark scheme yet. Let's see. Yeah, the mark scheme says that you should mention that the EMF produced is an alternating EMF, which does make sense based on the diagram. I did not mention that in my solution. But it did refer to the diagram because in the coil, the area vector is at right angles to the magnetic field, and since if you take the first derivative with respect to time of the flux, you get NBA omega sine omega t, or NBA omega sine theta. Sine of 90 is 1, so that's the max EMF that you're going to get. I was thinking that the alternating current would be implied, but that is true that you should probably mention, if we're going to mention all of that, I should mention that the EMF and therefore the current will be alternating. Now, I'm glad that I found that max EMF equation right there, because I'm going to need that for double I. And I'm out of space, and I did not include the answer area, so I'm just going to do it down here off the page. Oh wait, I misread double I. It doesn't want the coil, it wants for a single wire between A and B. This is a throwback all the way to the beginning of the topic. It actually goes back to 11.1. I was about to go off and find what the angular frequency is based on the linear speed of the coil. That would have been super annoying. Doable, but annoying. But instead, I can just do EMF is BVL. I know the speed, I know the length of the wire, and I know the strength of the magnetic field. So there we go. I think that's a much easier way of answering that question. It's also what the mark scheme tells me to do. But yeah, that's from 11.1. And then 3, or triple I, that wants the peak EMF covering the entire coil. So really only the portions of the wire that are chopping the field lines actually count towards the production of the EMF. So what do I mean by that? A, B, and C, D will be chopping the field lines. They matter. A, D, and B, C do not chop the field lines, so they don't count. So I'm not going to include them. So really I have the rotation of two straight wires that are actually, if I'm going to use the previous equation where EMF is BVL, I'm going to be counting those two wires for BVL in terms of the EMF produced. So each wire has an EMF of 0.058 volts, and there are two of them. But don't forget the number of turns in the coil. It says there are 80 turns in the coil, giving us 9.3 volts for the entire coil. And that's it.